I'm in the middle of writing a Mancala game, and I'm going to use that to introduce two new libraries I've written, both in Nim, called Turn-Based Game and Negamax. First, a little bit of background. About a year ago, I made a mobile game app called Kalah Mancala, and it's doing fairly decently on Google Play, but I'm wanting to make some upgrades to it, and I've decided this time around I'm going to change it from Python with the Kivy framework, which I wrote it in before, and move it over to Godot framework with nim coding for the AI and for the game rules engine. So this video is about me converting my code that I've already written in Python over into nim, which is for those not familiar with nim is a transpiler that converts a Python style of coding over into C, which then is, of course, compiled into object code. Now, when I wrote it in Python, I used a game rules framework as well, written in Python that included the Negamax algorithm. In fact, I wrote a version of the Negamax algorithm for that library, so I got heavily involved with that library called Easy AI. And what I wanted to do when I switched this over to nim is not just write my new game in nim, but also move those two libraries over at the same time. So that's what these two libraries are. The first one, and we're covering in this video, is something called Turn-Based Game, which is the game rules framework. It's actually how you design a two-player game in a very structured manner with a certain set of rules and conditions so that it could be used by other libraries such as Negamax or, say, a web framework or a mobile app framework later on. It's a common source of rule descriptions. And so that's what we're going on today. And then in the next video, we're going to cover the Negamax algorithm, which runs the AI that plays your opponent in the game. This should be fun. To get started, of course, you'll have to have both nim, the transpiler, but also you're going to need the library, Turn-Based Game, which the Nimble package manager can get for you with Nimble install Turn-Based Game. Now let's go take a look at the big picture of all this. Starting at the top, of course, we import the Turn-Based Game. That's what we see here. And then here we inherit from an object that we pulled from that library called game. So Kalah, which is the, just you know where that name comes from. There's actually over 200 ways to play Mancala. We're playing the Kalah rule set, which is the type most commonly seen in North America and Europe. The most popular form actually is Aware, which is played heavily in Africa and the Middle East and in Asia. And I'm thinking of writing a version for that later on too. But for now, we're concentrating on the Kalah rules. I'm going to put a link in the doobly-doo explaining how to play Kalah. And so if you're not at all familiar with the game, go watch that video, pause this one, watch that video next, and come back to here so that you kind of have an idea of what we're looking at. But the first step, of course, is to make a copy of that game object. And then there is a group of about 6 methods, scroll down here, that we override. There's actually quite a few methods in the library, but we modify setup, which is how we set up a new game. We override set possible moves, which is how we get the current moves possible at the current point in the game. We override determine winner, which determines whether the game has been won or not, and who is the winner if it has been won, or if no one's won, a state of stalemate, or essentially a tie. Then you have another method we override called make move, which in this game is really long. There's a lot to it. And then a method of status, which simply on the screen displays the status. Actually, this one's optional. You don't have to use it. But if you're going to play the game on the console, say for debugging purposes, which is what I'm going to do, that's a really useful thing. And then you invoke the very class you just created or the object you just created. Set up the players. Here we got 2 players named A and B. Pass it in the setup. And in this case, I'm also passing in the number of stones available in each pit. And again, watch that video if you don't know how the game's played. Otherwise, this is not going to make much sense. And then you play the game. And let me just show you what it looks like when you play it. Let's go ahead and compile it. And then we'll go into a little bit of the details of what's going on. Oh, sorry. All right. And what we're seeing here is it's currently person A's turn, the first person's turn. We see a copy of the board. And here we see the holes around the board, the pits. And we got 4 stones in each pit, none in the stores, which is where you keep the stones that you're winning with. This is the AI side, this is the user side. Right now, I don't have the AI turned on, so ignore the word AI. It's user versus user. You'll see that in a second. And then that possible moves routine comes back with a list of strings representing what kind of moves you can make. Now, because there's actually an international standard for how you label these holes, I actually have them labeled that way. Although internally, that's actually just simply a numeric array, and I just converted them to letters and vice versa. So possible moves here are F, E, and then all these combinations, C, B, and A. And when you see 2 letters in a row, essentially this is a multi-move move. So in the game of Kalah, if you choose D here, which has 4 stones, you drop 1 stone in each pit, 1, 2, 3, 4, and you end up in your own store. And when you do that, per the rules, you get to go again. So you can actually then go D or F, D, E, D, C, D, B, D, A. Those are all the other possibilities. I'll go ahead and go D, A. So here you see it. The result is now B's turn, but we can see the change in the board. A went, let's see, we did D and A. So D went, dropped, put a 1 point in here, and then A went, which pulled from here, and then dropped and put some stones on the other side. So now the score is 2 versus 0. And now it's B's turn, and they can do something. I'll just choose A. And then now it's A's turn, and you can see there's actually quite a few combinations now possible in the game. When this was written in Python, you could get pretty exotic as far as what types you can return, but because Kalah is a compiled language, you have to be much more strict about types, which is why I use strings in a lot of places, where in the Python world I could say just return anything. You know, you want it to be a dictionary, fine. If you want it to be a string, fine. If you want it to be a tuple, that's fine too. And you can do anything you want, and then I would just manipulate it in a generic fashion. But for this library, I'm using strings in quite a few places. So this is in fact a list of strings. Let me hit quit here, and let's go ahead and take a look at the actual code. This is all documented in the GitHub repo on the wiki, so you don't have to take my word on all of this. Now, this is a slightly more complicated version than what you'll see in the examples on the repo, because I'm actually doing this for full production. So I actually have a settings screen I'm starting to build out. So I have settings that are associated with the game. So I have a settings tuple, and here's the things you can set in there: stones per pit, scoring method, end of game rules, capture rules. Because like I said, there's a lot of variants out there. So even for Kalah, there's about 20-something variants you can have for that game. So there's a lot of combinations out there. Just for my own internal documentation, the board itself, here's the board, is added to the game object, and it's an array of 15 items. And I show 0 through 14 being assigned, 0 being the hand. So when you move stones, it actually is held in your hand briefly as it's being dropped. And then here's 1 through 14. There's this, and then here's a character map, so that when I can convert from the index in here to the letter that I would use to represent that place within the array. I'm not going to go into too much detail, so I'm going to skip over some of this stuff. Some of this, here I have an array of tuples, which is just a convenience thing. Rather than always calculating how far you are away from the next thing, or what the next house is, or excuse me, or pit is available, I actually pre-code a lot of that statically into here. So that I could, for example, if I want to know pit 4, who's the owner of that pit? Is it the user or the AI? I can just look up pit 4 owner and get the result back. And so let's go ahead and take a look at our rules. Here's some interim procedures that I'll use later on, but here I'm overriding the methods. So on setup, I'm calling the default setup, which is part of the game object. We also have settings. I'm setting stones per pit based on what I pass in here per pit. I have setting the hand to 0, because nothing's held in the hand at the beginning of the game. I'm setting the stores, that's the pits at the very end where you have your stones accumulate, to 0, and then of course I'm setting all the stones, putting the correct number of stones in each of the pits. Setting possible moves. Here I set it to empty, and then I recurse moves. That's a complicated thing, but basically I'm seeing what's immediately possible, and then based on each of those settings immediately possible, see if there's more possible moves, so that you can actually have, I've seen as many as 8 different sub moves you can make in a single move, where you actually do a lot of combination as a single selection. But this library is written in such a way that you have to have a fixed number of possible moves for any one game. Now this works really well for most games out there. Chess, checkers, reversey, all kinds of nim itself, actually, if you want to play the game nim in nim, all that stuff. Basically, most abstract strategy games will work with this because there is always a non-infinite number of possible moves for any one play of the game. And then we have a routine that simply passes, that determines who the winner is, and it doesn't return a value. This is a void. What it does is it sets an internal variable, which is winner player number, to a value. And it's either stalemate, which happens to be a -1, no winner yet, which is 0, which means the game needs to keep playing, and then or setting it to player 1 or versus player 2, or whatever the player number is. Turn-based game does allow for many players. It's not just limited to 2. You could have 50 if you wanted to. Really no limit to the number of players. Now, when we go to Negamax, we'll find out that's limited to 2 players. But for the game structure as a whole, you can do whatever you want. Now, this routine, set possible moves, returns a sequence of strings. One of those is chosen to make a move with, and then it's passed in here, and there it actually makes the move. And how that's implemented depends on the machine. But as you can see here, I'm taking each character, I'm calling it a sub move, in move, and then looping through it and following the rules. I scoop up the house chosen, I put it in my hand, and I drop 1 seed or stone, it depends on how you word things in Mancala, into each of the pits as it goes around the board. And here we can see I'm using that array of tuples. P of current pit next, so I can just find out what the next pit is. Because it's different based on who the player is. Because if you're again, getting back to the rules of Kalah, if you are, when you're going around the board, you go through your store, but you don't go through the opponent's store. So the sequence is different based on who's playing. So this really makes things simple for both reading and for debugging. We can handle captures, and here I'm actually handling different kinds of capture rules. There's no point in going through that. Right now, we're just going to go through the standard capture rule, which is you capture the opponent's stones if you land in one of your own pits that's empty. But there are also variants on here, so I've coded some of those variants. The end of game move, if you actually end the game, there's a sweep move by default. But again, there's variants out there. So I handle empty player sweep, and a few other combinations, 4 different combinations of rules. But that's all encoded in the make move command. Move, and then here's status here, so we can actually play it. And then down here, play. Essentially, if you look in the library itself, what play does is it actually just goes through and switches players, asks what moves are possible, puts it up on the screen so you can type it in, goes on to makes that move, sees if the game is over. If it's not, then it continues the loop, and it just runs through the loop. By itself, turn-based game doesn't save you a whole lot of coding time because it's not that extensive of a library. It's mainly useful as a means of very specifically establishing the different parts of the gameplay so that you can use it with other libraries. And that's what we're going to get into next, which is the Negamax library. If you like what you see, please subscribe. Thanks for watching.